Hi everyone, this is the last lecture for this class, and what I wanted to do in this last lecture is give you an overview about quantum complexity theory. So, one lecture is obviously not sufficient to do justice to this subject, and so in parts the lecture is going to be very, it's going to be very sketchy. I'll sort of sketch for you a picture of the subject at a high level, and I don't really expect you to follow all of it or even much of it, but if you get a sense of what the subject is about and whether you are interested in it, I'll feel that's a successful lecture. Okay, so try to follow as much as you can, and if you can't, you can skip past most of this, or just get a sense of what the subject is about. Okay, so in the first part of this, in the first video, I'm going to talk about the lower bound for quantum search and what it tells us about quantum algorithms for NP-complete problems. Okay, so remember what the search problem was, the unstructured search problem. So we think about having, we are looking for a needle in a haystack, or a digital needle in a digital haystack. So our digital haystack is a table with capital N equal to 2 to the little n entries, and one of these entries is marked, and so this is the proverbial needle, and we are searching for this entry. So we said that there's a theorem that in the last lecture that any quantum algorithm must take at least square root of n time. Actually, what we meant by square root n time is it must make at least square root of capital N queries to this table. And since square root of capital N is 2 to the little n over 2, this is exponential time in the length of the input. So let me again say what our setting is. We think of this table as being specified by some circuit. So some circuit that computes some function f, so that on input x it outputs f of x, which is either 0 or 1, so it's a Boolean function. And f of x equal to 1 says that x is a marked element, and 0 says it's unmarked. So the length of the input x is an n-bit string, so the length of x is n bits. And so the running time, the number of queries, is exponential in the length of x. Okay, so how do we prove such a theorem? So first let's show that using one quantum query, there's no quantum algorithm that can guarantee a success probability larger than some constant over n, probably 4 over n. So here's how we argue this. So let's perform a test run with an empty haystack. By this I mean that there's no marked element in this haystack. Okay, no marked element in this table. And now suppose that the algorithm makes this query sum over all x, alpha x, x. Now remember, for this to be normalized, the sum of alpha x magnitude squared must be equal to 1. So there's some alpha, so there's some x such that alpha sub x squared is less than or equal to 1 over n, right? Just by averaging. In fact, if we pick a typical x, it has this property. Okay, so now what we do is mark that element. So we mark that x for which alpha x magnitude squared is small as possible. So now when we make this query, when the algorithm doesn't know where the marked element is, so it of course, once we put the marked element there, it still makes the same query. And so it queries the marked element with amplitude, with amplitude, so the amplitude with which it queries this particular element, let's call it x star. The magnitude of the amplitude is at most 1 over square root of n. Okay. And so now what we're going to argue is that the final state of the algorithm, if you look at the quantum state of the algorithm, so if you have the quantum algorithm, you look at the final state psi, which you are now going to measure. Well, psi was something when, psi had some value when we perform the test run. And now what we're saying is psi cannot be changed by very much. When we actually run it on the table with the marked element, it can change by at most 1 over square root of n in Euclidean distance. And so what that implies, if you work through it, is that the chance that your measurement outputs a different value than it did in the case of the empty haystack or the no marked element is very small. It's smaller than constant over n. It's smaller than some constant times the square of this value. Okay, and that shows that one quantum query cannot possibly help. So now, what we'd like to do is we'd like to generalize this particular argument to many steps. So suppose our algorithm now makes, so our quantum algorithm makes t steps for some t. Now how does the success probability of the algorithm vary? How does it increase as t increases? So what we're actually going to show is that the probability of success is going to grow only as t squared over n. And this is why, if you want any significant success probability, you have to use t to be about square root of n. Okay. Now the argument for doing this is very similar to what we did in the previous case where we had only one query. So what we're going to do is perform the test run with the empty haystack, so no marked element. So run, whatever algorithm we have, we are going to show that there's some marked element such that if some location, so that if the marked element is there, then this algorithm is going to do badly. It's going to succeed with probability at most order t squared over n. So what do? We do the test run with the empty haystack with no marked element. Now we find that element which is queried with the minimum squared amplitude. So we look at every step and we see with what squared amplitude does the location x get queried over all these t steps. And we find that x for which this is minimized. And now we we call that particular x star, and we make that the marked element. And now what we'd like to do is we'd like to show that, in fact, if we now run our algorithm on this particular table with this particular marked element, then the quantum algorithm is unable to distinguish this from the empty haystack case, except with very small amplitude. So the final state of the algorithm is almost indistinguishable from the case where there was no marked element. Now the difficulty in doing all this is that the subsequent query amplitudes change depending upon previous answers. So as the algorithm runs, it doesn't make, its subsequent queries do not act the same way that they did. The queries don't look like what they did when we did the test run. They now diverge more and more. And in fact, one might even suspect that they diverge exponentially. So what we have to do is show that the queries, somehow the run cannot diverge very much. Okay, so I don't want to spend too much time on this argument, but I'll just give you the gist of it. So this is what's called the hybrid argument. It's proved by what's called the hybrid argument, which is one of the very basic arguments, ways of bounding running times of quantum algorithms. So the first thing we do is we spread out the quantum circuit so that only one gate is being applied at a time. Now, of course, in the quantum circuit, maybe there are many gates acting in parallel, but then we can always delay some of the gates. So if there are 5 gates acting in parallel, we could just have one of them act first, and then the second one, and then the third one, and it makes no difference to the actual workings of the quantum circuit. It only delays the output. It makes it run slower. But we don't care. We have plenty of time. So here's our quantum circuit. It applies some unitary U1, and then some unitary U2, U3, U sub t. But now there's one other aspect that we really must fix, which is this a test run, or is this the real run of the algorithm? So let's say that we have our function f, which is identically 0. So this was our test run, and then we use this to identify a function f prime such that f prime of x star equal to 1, and it's 0 everywhere else. So this was our real run of the algorithm. Okay, so let's say up here we have the test run. So whenever it calls an oracle, whenever it calls f, so that's the test run. And then down here we have the real run of the algorithm, where whenever we make a query to f prime. And what we'd like to do is we'd like to say that the output here, the output state here, psi prime, is very close to the output state here, psi. These two are not very far from each other. And so the way we'll do this is we are going to modify the test run into the actual run one step at a time. So what I mean by this is that we'll do a run where everything looks like the test run, okay, except that the last step is done as though we were doing the real run of the algorithm. Okay, so now what we want to do is we want to say, how different is this output psi 1 from psi? And the answer is, well, it's very much like, there's only one query that's changed between these two runs. But we know how to analyze one query. All it does is it changes the output state by roughly 1 over square root n. So in other words, what it did was, if this was the output state psi, then what it did was it changed it to some new state, which is roughly 1 over square root n away from the old one. In some direction, we don't know in which direction the change is, but it's at most 1 over square root n away. So now we repeat this process and we do one more run, which still looks almost like the test run. Except now the last two steps look like the real run of the algorithm. So we make queries to f prime. Okay, so now how different is this output, psi2, from psi? Well, in order to analyze that, let's just understand how different is psi2 from psi1. Well, the only difference between these two, of course, lies in one step. Okay, so we know how different the output of this one step is in these two cases, at most 1 over square root n. But this is not the last step of the algorithm. So surely this is a different situation. So we can say that before the last step of the algorithm, the input to the last step of the algorithm in these two cases differs by at most 1 over square root n. The input vectors in the two cases differ by at most 1 over square root n. But now remember this, there's this crucial fact about quantum computation, which is quantum evolution is unitary. Meaning this last step, whatever it was, it's the same in both cases. We are applying the same unitary transformation. So if we give two inputs which make a certain angle with each other, then this last step is going to preserve that angle. So it's going to preserve the distance between the two vectors. So psi1 and psi2 are going to differ by at most 1 over square root n. Again, we don't know in which direction, but we know that they can be at most 1 over square root n apart. So we proceed this way, making one change at a time until we get back to the original, the actual circuit. And we realize that our state moves in t steps, where each step changes the state by 1 over square root n.